we're on a planet that's getting bombarded by meteorite impacts. The problem with the volcanic eruption is the gases that it releases, which change the climate and the ocean chemistry.
Is there enough evidence in terms of chemical weathering as for humanity to be worried about potential mass extinction?
One of the challenges that we experience in the modern world is that as you warm the planet, you melt the ice. There's less ice. The ice helps keep us cool by reflecting sunlight into space, and whereas you melt ice, you absorb more of the sunlight, which warms the planet, which causes more of the ice to melt, which causes you to absorb even more of the solar radiation, which causes more of the ice to melt. If you want to understand if you're at risk of landslides, or if you're at risk of volcanic eruptions, if you're at risk of earthquakes, if you want to provide resources to your people, if you want to make your people safer, if you want the future to be better for your community, understanding geology is essential to doing those things. The other reason that it's important is that all of our resources come from the earth ultimately. Learning, it enriches your mind. It's fun. It makes you more interesting. It gives you a way of making a difference in the world. If you care about your kids and your grandchildren and their children, geology is not going to save us. It's up to us to save us.
Hi, friends. Today we're visited by Jonathan Payne, who is a professor of geology at Stanford University. John, thank you so much for gracing our show.
Great to be here.
Tell us about yourself. You grew up in New York and decided to just be fascinated with geology after you started figuring out about the dinosaurs and all that.
Yeah, so I grew up initially in a town called Hamilton in upstate New York, and then later in a town 20 miles down the road called Clinton. Both towns of a few thousand people. And my interest in the natural world and the outdoors, I think, started because I lived in a very small town on a dead-end road and spent most of my time outside the house running around, just enjoying running around in the woods and building forts and things like that. In terms of geology in particular, I was fortunate. My dad was a university professor, a history professor, and one of our family friends was a geologist. He's actually a geochemist, and so was interested in the acid rain problem that was very important in New York State at that time. But in terms of what you could do with kids, in upstate New York, almost all of the rock there is marine rock that's over 300 million years old, and has the shells of ancient animals that lived on the seafloor at that time. And so when farmers were digging into the hillsides, essentially to make gravel to put onto the farm roads and things like that, they would quarry through this rock and it would bring out lots of fossils. And so our friend Rich April took me and my brother and his kids out to some of these quarries with my dad as well sometimes. And we would just go in and collect the fossils. And to me, it was just really amazing, right? To see the shells of these animals that had lived a really long time ago. I remember sort of being confused and not really understanding how the ocean could be, over all these hills that we lived in, and certainly didn't understand, right, that the hills are a very young thing, right, that they're cut through all of the layers of marine sediment. So as a kid, I think from that experience, understood that the Earth was really old, that there were these animals like trilobites that are completely extinct, that I could find in the rocks. And I was definitely fascinated with the idea of trying to understand, what was the world that they lived in and how was it different from the world that I was living in. And I think part of that was just, living up on this hillside with a view over a lake and everything, and trying to picture that this was at some point it was underneath the ocean, right? And so so I was fascinated by that. I think other things that I remember from that time in terms of geology, I was 5 years old when the paper came out that first hypothesized that, or first argued convincingly that the dinosaurs were final dinosaur extinction was caused by the impact of an asteroid. And I remember that being on the news, and so it was one of the early things that I can remember. Also around the time that there was an assassination attempt on the American president Ronald Reagan at that time. So these are some of the early things that I can recall of sort of world events. And so it definitely made an impression on me because I was interested in dinosaurs at that time, like a lot of 5-year-old boys and girls. But I wouldn't say that I went through high school on a mission to become a geologist, right? I enjoyed the outdoors. I enjoyed the natural world. I wanted to understand it. But I didn't know for sure what I wanted to do with my life at that point.
Geology, for people like me,
it's
just like on a different level. Mm-hmm. What would it take for the young kids going forward to see or look at geology as something that's cool, that's important? Because I don't know a lot of geologists, to be quite honest. And I'm not aware of many of my friends in schools. That would have been, there were one or two, but most others just found it very difficult to get interested. I think for the mere fact that it is not easy, right? As a subject.
I think for me, geology came out of just sort of basic fascination with the natural world, that I just wanted to understand, where we came from, where I came from as a person, where we came from as a species, where the Earth came from, right? How did it all start? Right. I think these are the kinds of questions, right, that every world religion tries to answer, that many natural science disciplines, help to answer. And so it was really that basic curiosity that got me into it. I think, and that's certainly one reason to be excited about geology, is just that you live on this amazing planet, and to be able to go outside, and whether you see an animal or a plant or a rock, to understand that all of those have stories to tell about the history of the Earth, right? That our genes tell a history of our species. The genes of a plant tell a different story, that if you put those together, you start to understand our common ancestry. And if you see a rock, the minerals that you see in the rock, the fossils that you see in the rock, tell you whether it came out of a volcano, whether it's an ancient sediment from the bottom of a lake or an ocean, whether it's a rock that has been buried very deeply and then brought back to the surface over time by tectonic activity. But the other reason that it's important is that all of our resources come from the Earth ultimately. And so if you are using a cell phone, it has metals and rare earth elements that have to be mined out of the planet. And you won't know where to get those if you don't know any geology.
We got a lot of those in my country.
Geological hazards, right? If you want to understand if you're at risk of landslides, or if you're at risk of volcanic eruptions, if you're at risk of earthquakes, you have to understand the geology of the region. And so it's also an extremely practical discipline, in the sense that if you want to provide resources to your people, if you want to make your people safer, if you want the future to be better for your community, understanding geology is essential to doing those things, right? And that isn't why I went into geology, but I've come to appreciate just how important all of that is. That the entire industrial revolution, right? The reason that we don't all live as peasant farmers anymore is that we understood geology, and we understood resources we could take out of the planet and put to use. One of our big challenges, right, is that the way we've been able to improve standard of living for many peoples is to produce a lot of energy. The main route that we've produced that energy historically has been burning fossil fuels. The really big positive benefit of that is our ability to improve the lives of people in the short run. The downside is the waste product, the carbon dioxide, ends up in the atmosphere for hundreds of thousands of years in a geological sense, and makes quality of life worse for future generations. And so now we have a different problem that we need to address.
You made a decision to teach in high school, which I thought was really cool. Because, I come from a region where, admittedly, the educational attainment is not as high as it should be, with the exception of one or two countries in Southeast Asia. And it's predominantly on the basis that most of the households, the heads of the households don't have tertiary education, right? And the only way to disrupt that in a positive manner is to really have good teachers at the schools. What made you decide to teach in high school?
Yeah, probably a few different factors. One is that I come from a family of educators. My dad, as I mentioned, was a history professor. My mom was a math teacher. My grandmother was an English teacher or English professor at a community college. So my brother now is a university professor of mathematics. So education was what my parents did. My dad referred to it as the family business sometimes. So there was that, right? That it was what was role modeled to me in my household. And it was clear that my parents enjoyed it. They enjoyed learning. They enjoyed teaching. They enjoyed making a difference for students. I also benefited from having terrific teachers myself, right? Who inspired me with the impact that they had on me. In particular, I had an English teacher in high school, Debbie Hepburn, who was amazing not only in communicating sort of the technical skills of how to read and how to write, but more importantly, communicated the passion of what you could learn and what you could do with the knowledge if you could read books and you could read articles and you could understand them.
Right.
And that, I think that message, like the message I got from my parents of learning, it enriches your mind. It makes you more, it's fun. It makes you more interesting. But it gives you a way of making a difference in the world. And so if anything, I would say, I probably became a geologist in order to teach rather than teaching in order to become a geologist, right? People have asked me, if you didn't have this job, what would you be doing? And it's hard for me to imagine doing something that didn't involve teaching.
Right.
I've coached high school sports. I've coached my daughter's middle school volleyball team.
Wow.
I love coaching too, right? It's the same thing.
How would you fundamentally differentiate between teaching at a high school versus teaching at a university?
Right. So I guess I can give you or your listeners a little bit of background. So after I finished college, I already knew that I wanted to go to graduate school at some point, but I didn't know exactly what I wanted to do. But I did know that I liked to teach. I had already been a TA in class. I had been a overnight camp counselor. I had tutored in the math and science tutoring center as a college student, and found out that there were these opportunities to teach at boarding schools internationally, which could satisfy both my interest in being able to travel and see the world and my interest in, I needed a job and my interest in teaching. And so applied to a number of boarding schools to see if I could get a teaching job, and ultimately got one at the American School in Switzerland, which is in Lugano in the southern part of Switzerland, the Italian-speaking canton of Ticino, and taught. So I was a dorm parent, so I lived in the dorm with the students. I taught middle school science to 7th and 8th graders. I taught introductory physical science to 9th graders, and in the second year, I taught Algebra 2 to mostly 10th and 11th graders. So I had a range, from 7th graders up to even a couple of seniors, I think, in my Algebra 2 class, if I remember right. So in terms of what's different, right? And so I did that for 2 years, went back to graduate school, and have now been at Stanford. This is my 20th academic year at Stanford.
Condolences or congratulations?
A little bit of both. I would, at a base level, I think that it's all the same, right? That you are trying to reach students, you're trying to give them skills to be able to do whatever subject it is that you're teaching them. But even more than that, you're trying to inspire them, to show them why it's important to know about the world, to show them that they have power to change the world with their knowledge, and that knowledge is power, right? And that is the same, I think, whether you're teaching a 7th grader or a postdoctoral fellow, right? People are at very different developmental stages, and come in with very different amounts of background knowledge and skills, if they're in 7th grade versus high school versus college versus graduate school. And so you have to adapt your style, right? You have different amounts that you expect students to do independently versus in class. You have different amounts of prior knowledge that you can assume. With my graduate students, I can assume they know calculus, which allows me to do things that you can't do with a 7th grader. Not because the 7th grader isn't smart, but because they haven't had time to learn calculus yet. And so the skill set changes depending on the age of the students. For me, one of the biggest challenges when I was teaching at the middle school and high school level was actually I found the middle school much more difficult than the high school. And it was because I was not good enough at controlling the classroom.
Yes.
Right. And this is not the student's fault. This is a mismatch between my skills and what was needed, which is that at the developmental stage of a middle schooler, right, they're learning adult social interactions, right? They're transitioning from becoming little kids to becoming adults. And they're experimenting with behaviors and trying to figure out how do older people interact with each other. And I just wasn't good enough and didn't have enough skills yet to manage a classroom like that. And that made me less effective as a teacher, not because I didn't know the technical material, but because you can't teach any technical material if you can't get the kids to sit in their seats and pay attention. What I found was I was more effective with the high school students who were more able to sit and listen and needed less classroom management, more content delivery. And that made me optimistic that if I could go and teach college students that, that I would have less classroom management to do and a lot more content delivery to do. I think that even at the college level, right, the different colleges have different populations. Stanford, as a very selective university, the students that we bring in generally are very motivated. Many of them have had a lot of opportunities coming through school. They've had in many cases, a lot of resources, that not everyone. But in general, I have students whose skill sets are strong and whose motivation is very strong. Yeah. And so I can really just focus on the content delivery. Yeah. In other situations, you might be coming in with students who didn't get as much math and science as they should have. And so you need to fill those gaps while you're trying to teach the introductory geology. Yeah. In general, my view is that's not the student's fault. That is the educational system's fault, that we don't support all of our students as well as we should. And so people come out of high school sometimes without as strong a skill set as they really should have. Not to say that there's no responsibility on individual students. There absolutely is. But all of us, in listening to my story, I think it's very clear, right? All of us are products of the environments that we come through, and we're deeply influenced by those.
I agree.
And so we need to create better environments for our students if we want better outcomes.
I agree. I tell my students and friends that it was my middle school teacher, my high school teacher, even my elementary school teacher that had a profound impact on me, my decision making. Not to discredit my university professors, but it was the earlier education, professionals that would have had a much more impact on my life, which I think underlines the point that it's important to have really high quality teachers at the most rudimentary levels, right? As to help shape, society, into whichever direction you want it to. And I come from a region where there hasn't been, nearly as much investment as needed, for creating good professionals within the elementary schools, all the way to high schools, as to prepare the students, for the tertiary levels. Now, I want to ask you about the, Paleozoic era, the last 500 million years. But before that, explain how oxygen was not around the first 2.3, 2.4 billion years, ever since planet Earth was, created 4.6 billion years ago.
Yeah. So, I guess a couple of key facts, which hopefully all of our listeners know, but if they don't, this is a great chance to learn.
Yep.
Right, the Earth is about 4.56 billion years old, and we know this largely from dating meteorites.
Right,
and we know from the geological record, we have rocks that go back about 4 billion years, and we many of the very oldest rocks have been buried very deeply. They've been heated up. They've been altered in ways that make it a little hard to have direct geological evidence of what the very earliest part of the planet would have looked like. We know a lot of that more from theory than from direct observation. But by the time you get to 3.7 billion years ago, we have rocks that formed as sediments, right? So the same kind of material that you'd find at the bottom of a lake or the bottom of the ocean or in a riverbed, we have those kinds of that material turned into rock all the way back to 3.7 billion years ago. And by looking at what minerals are in that rock, and by looking at the detailed chemistry, for example, the isotopes of different elements, right? So many elements have more than one version. So it's the same element, it's still oxygen, but it has more neutrons in the nucleus, which makes it go through chemical reactions a little bit differently. For example, if we think about oxygen 18 versus oxygen 16, we can measure many of those different things in these ancient rocks. And when you put those all together, what they tell you is that there was no oxygen in the atmosphere up until about 2.35 billion years ago. So for about the first half of Earth history, there's no oxygen in the atmosphere. And we know this because there are mineral grains that react very, very quickly the minute they're exposed to oxygen in the modern world. So you almost never find them in transported down rivers and in the sediments that end up in lakes in the ocean. In these very ancient deposits, we see those. They end up in rivers and they're not reacting with oxygen. They're just moving around like a quartz sand grain. There's also some other details of which elements get pulled out of soils that change if you have oxygen or not, right? And in our modern, probably the most obvious thing that most of our listeners would know is that if you have any iron metal, it rusts, right? If you get any water on it, it reacts with oxygen to make an iron oxide, and that's what rust is. There was no rusting of the Earth, essentially, for the first 2.5 billion years. And that's what we see geologically. Then you start to see a change where things start to rust a little bit. You get iron oxide minerals in your soils. These mineral grains that were preserved all of a sudden stop being preserved in the same kinds of deposits. It turns out we've been able to quantify this a lot. So people have known that for many decades. It was only after the year 2000, very early 2000s, that we developed a more quantitative measure, which is that if you look at which isotopes of the element sulfur are in sulfur-bearing minerals, there are different ways that the isotopes are mixed together if they go through photochemical reactions in the atmosphere versus reactions in water. And the preservation of the photochemical reactions depends on essentially not having oxygen around, not having an ozone layer. Those signals are preserved up until the rusting starts. And the minute the rusting starts, those go away. And that tells us that we went from having like less than 1/100,000th of the amount of oxygen that we have in the atmosphere today to having more than that. So it gives us a little quantitative threshold. There's then lots of more complicated geological evidence. And we don't know exactly what the trend is in oxygen other than it became measurable 2.35 billion years ago. It was probably much too low for us to breathe. So if you had a time machine and went back, there was oxygen, but you would suffocate. There's not enough oxygen for you.
Right.
And one of the big arguments now is, or debates in the evolution of animals, is from 2.3 billion years ago, where we first have oxygen, until somewhere between, say, 600 and 800 million years ago when the first animals evolved.
Right.
Were they limited by too little oxygen? Or was there enough oxygen, but other factors prevented the evolution of animals, that you just didn't have the genetic toolkits that you needed to make organisms like that? And so there are a lot of geologists doing work now trying to find better ways to put numbers on how much oxygen was available from 2.35 billion years ago up into the early evolution of animals.
What would have brought about the very existence of oxygen?
Thanks for asking that. So oxygen at Earth's surface, the reason we have oxygen in the atmosphere is biology. In the modern world, most of that oxygen is produced by the green plants that we see outside and by algae that photosynthesize in the oceans. Initially, all of those photosynthesizing algae and plants have something in their cells called a chloroplast, which is an organelle that does the photosynthesis, that takes the carbon dioxide in, uses light, and produces oxygen as a waste product. When we go and study bacteria, which were the earliest organisms on the planet, what we see is that there are actually a few different kinds of bacterial photosynthesis. Only one kind produces oxygen. The other kinds photosynthesize but don't make oxygen as a byproduct. Those evolved earlier, and they're more limited by other aspects of the environment. So one way of doing this is to use sulfide. So reduced sulfur dissolved in the water as a way of getting your electrons. Then you're limited by how much sulfide is around. The oxygen-producing bacteria get their electrons from water. There is a lot of water at the surface of the planet. And so once they figured that out, they were able to take over as the most abundant photosynthesizers. And so really what we're seeing is that at some point before 2.35 billion years ago, this oxygen-producing bacterium evolved. And this turns out to be a really interesting story that I'm not deeply expert on, but it involved putting together two different pieces of photosynthetic organelle to do everything that needed to be done to go from having carbon dioxide and water to having organic matter and oxygen. So this is a big evolutionary event. It only happened once. So they start to produce oxygen, but there's lots of stuff like the rust that we talked about, right? Sure. Oxygen wants to react with things. And so just because you make it doesn't mean that it builds up in the atmosphere. Then you have to make it fast enough that it builds up in the atmosphere before it gets removed. And you essentially need to take some of the organic matter that's produced during photosynthesis and bury it in rocks so that it doesn't back react with the oxygen. Because if you imagine you make all these bacterial cells, you make the oxygen, then the cells die, the oxygen reacts with the cells to make carbon dioxide again. You're back where you started with no oxygen. So Earth is continually burying organic matter and leaving some extra oxygen behind. And so if we stopped photosynthesis today, over a few million years, all of the oxygen on the planet would go away because it would all react with minerals to produce rust and things like rust, other oxide minerals.
Talk about the 100 million year cycles in terms of whether or not you produce net positive or net negative carbon. How it affects the sea, also, acidification.
Okay.
If like within 100 million years, there's more carbon dioxide production as opposed to less, or net negative,
right?
It affects not just the climate but everything.
Yeah.
Right. Yeah.
Yeah. So, as you were saying, right, but carbon dioxide across geological time is the most important gas in the atmosphere for our climate. Right. That is there are other gases that matter, but carbon dioxide geologically appears to be the big one that drives the climate, which affects the habitability for animals and plants. When Earth formed, there is carbon dioxide deep in the earth, in the mantle, and through volcanoes, eventually that carbon dioxide is released at the surface and goes into the atmosphere. Eventually, geologically, that carbon dioxide is then removed from the atmosphere and put back into the solid earth, into rocks, in one of two forms. One form is calcium carbonate, limestone. Your listeners in Indonesia will be probably most familiar with this in terms of the coral reefs that form around tropical islands, right? And this is carbon removal as calcium carbonate. And so organisms are taking that material, mostly dissolved in the oceans, turning it into their skeletons and putting it on the seafloor. Even before we had animals that could make those skeletons, the pure chemical process will also form those minerals, calcite and aragonite, and put them on the seafloor. The other way that carbon dioxide is removed is by photosynthesis, turning it into organic matter, which can be buried. And that is what becomes coal, oil, gas. All of that is the remains of ancient life, mostly algae and plants. So over geological time, we have a competition between the geological forces that are putting carbon dioxide into the atmosphere from volcanoes and from the chemical weathering of organic matter and limestone, or in the modern world, the burning of fossil fuels, and then the processes that remove it, right? The deposition of calcium carbonate on the seafloor, the burial of organic matter. And geologically, that depends mostly on things like plate tectonics. So how fast are volcanoes cycling carbon dioxide out of the earth? How quickly are subduction zones taking sediments and putting them deep into the earth to remove carbon dioxide? How productive is the biosphere? When plants and animals die, are there places for the carbon to actually be buried? And this is one of the challenges, again, that if we think about in the modern, is one of our climate problems is the question of carbon storage, right? The carbon goes from being in plants and animals to being in soils to being in rocks and being removed. As we warm the planet, one of our worries is that the carbon in soils actually gets turned back into carbon dioxide and released back into the atmosphere. That's one big problem in the tropics. So for places particularly like Southeast Asia. Another is that it can come back as carbon dioxide. It can also come back as methane, right? And methane is a very important greenhouse gas because it's a strong greenhouse gas and because it operates on wavelengths of light that carbon dioxide misses. And so it essentially adds a different kind of blanket to the atmosphere to keep us even warmer. And so producing more methane out of tropical wetlands is another big challenge for us. Again, these are short-term problems. What I'm mostly talking about
are the
millions to hundreds of millions of years processes. And so we see the Earth's climate cycling. On those timescales, other things that matter are changes in where the continents are. Having continents at the poles is different than having continents at the equator, because at the equator, especially if you have mountain ranges, the carbon dioxide reacts quickly with minerals and gets removed ultimately as calcium carbonate as the sediments. In the poles, there's more ice, there's less water and rain. And so if you have continents at the poles, you actually get less of this chemical weathering, which can affect things. Then you get changes like ice, right? Ice reflects sunlight back into space. Plants and dark rocks absorb that sunlight and turn it into heat at the surface. And so we also, on geological timescales, have changes in what's called the albedo, which is just a technical word for how reflective our planet is, right? And so one way to cool the planet is to make it more reflective, to put things like ice on it. If you have a lower albedo, if you're less reflective, get rid of your ice. And this is, again, one of the challenges that we experience in the modern world is that as you warm the planet, you melt the ice. There's less ice. The ice helps keep us cool by reflecting sunlight into space. And so you actually get this reinforcing feedback, whereas you melt ice, you absorb more of the sunlight, which warms the planet, which causes more of the ice to melt, which causes you to absorb even more of the solar radiation as heat, which causes more of the ice to melt. And so you can get into these runaway effects. Right now, we're worried about runaways that would cause more and more warming.
Right.
It turns out there were massive climate events very deep in Earth's history, 800 to 600 million years ago, which we've referred to as snowball Earth events, where you essentially imagine the Earth as a big snowball, where we think this happened in the other direction, where ice sheets started to grow, reflecting more sunlight, which cooled the planet, which allowed the ice sheets to grow even more. And you actually got ice sheet growth all the way down to the equator. And so imagine being in Indonesia with glaciers coming right down to the ocean, right? Just a very, very...
It'd be nice. We could start skiing there.
You could absolutely start skiing there. It would be a problem if you wanted to build houses and things like this, right? So, one thing that I think geology really offers to us is just how different our planet has been at different times in its history.
Talk about the 5 extinctions and how each one is different from the other, going back to around 500 million years ago.
Yeah. So I guess a couple of things I should say, right? One is that when we study biodiversity in the geological record, the things that make really good fossils, a lot of that's plants and animals. And among plants and animals, the plants and animals that have hard shells, especially the animals that make hard shells, they preserve a lot better than worms, right? Animals that are purely soft-bodied, mostly when they die, they decay and get completely destroyed. Animals like clams or snails or corals produce big, hard skeletons, and those preserve in rocks and can last for hundreds of millions of years at least, probably billions of years. So animals with shells first start showing up on the planet about 550 million years ago. And especially the animals in the oceans, which is where animals first evolved, they preserve really well because the oceans are places where sediment is accumulating. And so when animals die, they get buried. On land, as many of us know, a lot of what's happening is erosion. And so if an animal dies on land, if I died on land, my body starts to decay. It doesn't tend to get buried. It tends to get transported because things are eroding around me. Yeah. And so getting buried is a little bit harder. So the things we know best is the diversity history of marine animals. Yep. And that goes back about 550 million years. So when we study mass extinction, almost all of these mass extinctions also come with extinction on land, except for the first one, because there wasn't really much of a terrestrial biosphere yet. There were no land plants yet, very few land animals. So our oldest mass extinction event occurred at the end of what we call the Ordovician period. That's about 443 million years ago or so. The most recent one happened 66 million years ago at the end of the Cretaceous. This will be familiar to a lot of our listeners as the extinction of the dinosaurs.
Sure.
But it had a major effect on marine systems as well.
Almost as much, right, on marine and land.
Yeah. Certainly, very, very similar in terms of the amount of impact. And so there are 5 of them. This End Ordovician was the first. then a set of extinctions in the late Devonian that are usually sort of lumped together as a late Devonian mass extinction. Right. An extinction at the end of the Permian period, 252 million years ago. Right. This is the biggest of the extinction events, essentially no matter how you measure it. If you measure it as the percent of species that went extinct, if you measure it as how different were ecosystems before and after, if you measure it as which were the dominant groups of animals before and after, how much did that change? Right. If you measure it as how long did it take to recover, the end Permian wins no matter how you do it. Yeah. Then about 50 million years later, about 200 million years ago, there was an extinction at the end of the Triassic period, which looks in many ways like a small version of the end Permian extinction. Right. Not in every way, but in many. And then there's the end Cretaceous, which actually in many ways looks different from the other four in terms of the patterns of extinction.
What would have caused each one of those? Meteors or volcanic eruptions?
Yeah, so this is one of the really interesting things is the first one, I think, where our best modern explanation sort of came to light is the end Cretaceous, the most recent.
Right.
And in even going back to the 1950s, there were sort of fringe theories that maybe impacts of asteroids and comets could cause extinction on Earth. By 1972, Nobel laureate in chemistry, Harold Urey, hypothesized this, but there was no evidence that it had happened. And so people speculated, some sort of wildly, some like Urey, not super wildly, but without data. The big change happened in 1980 when Lewis and Walter Alvarez and collaborators published a paper saying that they had gone to rocks that were deposited before, during, and after the end Cretaceous mass extinction. And they had found unusual concentrations of the element iridium in these sediments. And that was really important because iridium on Earth is almost all deep in the Earth. There's very little iridium at the surface. And so their idea was actually that they wanted to know how much, well, I guess let me finish the story and then I'll tell you. They answered a question that wasn't quite the question they were actually setting out to answer, which is really cool. And shows you how science, some discoveries are deliberate and some of our best discoveries are inadvertent. But always, favoring a prepared mind, right? And so what they argued was that they saw this big increase in the amount of iridium in this clay layer that coincides with the extinction event. And they said there's so much iridium in here that it can't be coming from the Earth. It has to be coming from somewhere else. And the best way to get it would be to take a meteorite and slam it into the Earth, have it explode, which is what happens when big meteorites hit the planet.
This is the Cretaceous, the 65 million years.
Okay. Yeah. And all this dust would go around the planet and you'd get a dust layer everywhere. And so they went and they showed that this showed up not just at the first place they looked in Italy, but they showed that they could find it in New Zealand and in Denmark. And then they did a couple of really clever things. One thing they did is they said, okay, let's figure out if this clay layer is the same thickness everywhere on the planet. We know the concentration of iridium. We can figure out the total amount of iridium. And then we can say, okay, if we had a meteorite, how big would that meteorite need to be to have this much iridium? And so they did a calculation and came up with a size. And then they said, we know that in impacts, most of the clay layer is actually going to be from the Earth. It's not going to be from the object that hit the planet. And in fact, the ratio is something like 60-1. So if you look at that clay layer, it's 60 parts Earth to 1 part meteorite. It's mostly the stuff on Earth that got blasted up by the object hitting the planet. And so they did the same thing where they said, okay, how thick is the clay layer? And if we figure 60-1, how big would the meteorite be? Right? How much mass was in that meteorite? And both of the answers came out in the range of 6 to 10 kilometers in diameter. So pretty big object.
Very big.
And we know just from sort of knowing how meteorites work that it would probably be moving at 10 to 20 kilometers per second when it hits the planet, right? And so for me, that means like where you and I are sitting in in Palo Alto, we could be in San Francisco in 2 seconds, moving at that kind of speed. So it is really, really moving fast. And so it has an enormous amount of energy. And this is what Urey had known and why he hypothesized that impact events might cause extinction. That if you go look at the moon, it's covered in craters. The only reason the Earth isn't covered in craters is that we have plate tectonics and erosion. And so it has been hit by lots of objects, but the craters get buried, they get removed by plate tectonics. And so it's not obvious to us when we look around that we're on a planet that's getting bombarded by meteorite impacts. So they calculate out the amount of energy. And essentially what you end up with is that it is hundreds of thousands of times more energy than the energy of all the nuclear devices that have ever been detonated. It is thousands of times the amount of energy that all humans consume in a year. And so if we directed all human energy consumption just toward trying to make a crater like the end Cretaceous crater, it would take us at current rates of energy production would take us thousands of years. And so this is just an enormous event. It creates a crater that's 180 kilometers across. And so, I don't have a good reference for you in Indonesian terms where we're sitting. We would get out close to Sacramento if we were on one edge of the crater, right? The entire San Francisco Bay Area fits easily inside that kind of crater, right?
Wow. What about the Triassic?
Yeah.
Was that also meteorite?
So this is the cool thing, right? Is the Alvarez paper sparked, not surprisingly, a big search among geologists. They said, okay, so it did two things. One is people said, okay, if you guys are right, there should be a crater, right? It took 10 years, but we found the crater. It's deeply buried on the Yucatan Peninsula of Mexico. It was initially discovered by the Mexican oil company because the structure underneath the ground looks a little bit like an ancient carbonate buildup of an ancient reef, which is what you would drill into if you wanted oil and gas. But when they drilled into it, what they found is all this shattered rock and figured out that they were drilling into an impact crater. And then once you knew what you were looking for, you could actually start making a map and see that the big tsunami deposits from this event are all in the Gulf of Mexico area. And that if you were in Italy or Denmark or New Zealand, you're very, very far from the site of impact, which is why you get a centimeter of clay and nothing else. And so you could actually start to figure out that even if we didn't find the crater, just by looking at the ejecta layers, you could play a hot and cold game of saying, okay, I'm getting closer because the impact layer is getting thicker and it's getting bigger objects in it. And I'm getting bigger tsunamis. And so we would have figured out more or less where the crater was, even if the crater had been completely destroyed. Turns out that it hasn't been destroyed. We can image it, and we've drilled holes in it now. So it took a decade or more, but we found all the evidence for the end Cretaceous impact, the tsunami deposits, the crater. People looked at isotope ratios in the clay layer, and based on the chromium-53 to chromium-52 ratio, we can actually map it onto a specific kind of meteorite called a carbonaceous chondrite. And so we don't just know there was a big object moving fast through the planet. We actually know which family of meteorites, and there are a bunch of different families. Based on the chemistry, we know which family this object came from. Not surprisingly, a lot of clever geologists said, well, if the end Cretaceous is an impact, I'm going to go look at the end Permian. I'm going to go look at the end Triassic. I'm going to go look at the end Ordovician. We've been looking for 45 years now. These other events do not look like they're impact events. They look much more like they were caused by Earth-based events.
All the other four.
All of the other four. Probably at this point, the best studied of these is the end Permian, the biggest one, which is what I've spent a lot of my career on. And through improved radiometric dating, looking at the decay of uranium in particular, we've been able to show that there's a massive volcanic province in Siberia, referred to as the Siberian Traps, which erupted starting just before, during, and just after this end Permian mass extinction event. It is the biggest volcanic province erupted in the last 500 million years. So that's on our side.
It would have been about 250 million years ago?
So it was about 250 million years ago. And So it's very, very big. But it doesn't cover the whole planet, right? These species were not driven extinct because they were buried by lava. The problem with the volcanic eruption is the gases that it releases, which change the climate and the ocean chemistry. So much more familiar to us if we're thinking about modern climate change kinds of problems. Then you say, okay, it's really big. Is that why it was important? That's undoubtedly part of it. It's really big. The second part is that on its way from all this material is coming hot from the mantle and getting to the surface, a lot of it's erupted. A bunch of it is just intruded into the crust and cools inside of the crust. And you ask, okay, well, what was in the crust? And it turns out that it happened to go into what we would call a sedimentary basin. So it has lots and lots of sedimentary rocks, kilometers thick. What kinds of sedimentary rocks? Well, it has limestone. Limestone is calcium carbonate. Carbonate is CO3, which when you heat it up becomes CO2. And so if you take calcium carbonate and get it to very, very high temperatures at very high pressures, you release carbon dioxide. We do something a little bit like this when we make cement, where we burn limestone to do this. This is another one of our major sources of CO2 emissions, right? Is making cement,
concrete, cement, and all that, right?
Yeah, because we burn limestone to do it. So you use lots of energy to burn it. And when you burn the limestone, you release CO2. This is happening geologically, right? Deep in the earth. In addition, there are salts in there. There's calcium sulfate, something we call gypsum or anhydrite. And there's halite, right? Sodium chloride, sort of table salt from the evaporation of ancient oceans. And there's oil, and there's coal, and there's gas. And so you get a few things. You get carbon dioxide release just from the magma itself. You probably get carbon dioxide release from heating up the limestone. You certainly get carbon dioxide release from heating up the coal and oil and gas. And then you get other weird things. You get sulfur volatiles, sulfate aerosols from heating up the gypsum and anhydrite. From heating the halite with petroleum around, you can even get chlorofluorocarbons, which are the molecules that have damaged the ozone layer over Antarctica especially, and caused our change in regulations of how we make refrigerant gases, right, for our refrigerators and air conditioners and things like that. And so all of this just produced by geological processes. And so what we think in the end happened is that we had a massive and prolonged global warming due to all the CO2 release. There may also have been actually short-term cooling events due to the sulfate aerosol releases. And there may have been big effects on the ozone layer from the production of chlorofluorocarbons. Then these become really challenging problems. Like you have to go in and use very high-tech equipment to try to look at little fluid inclusions in the magma, in what's left of the magmas in these volcanic rocks, to try to figure out, like, what were their gas contents? How much gas did get out? You have to do, field work in remote parts of Siberia to find rock samples where you have the magma or the volcanic rock now directly adjacent to the coals to figure out, like, how much of that coal actually burned when this was happening.
Give a worldly illustration about how the temperatures changed during the Permian event, and how the supercontinent Pangaea changed.
Right. So at the time of the end Permian extinction, this Pangaean supercontinent was pretty close to its maximum assembly. And so instead of the world we live in with a bunch of continents spread out, almost all the continents were together in a big sort of C-shaped
connected
continent. So you would have had a giant version of the Pacific Ocean, like even much bigger than our current Pacific. And then in the tropics, sort of like our Mediterranean Sea, you would have had a much larger ocean that we refer to as the Tethyan Ocean that would have been an east-west seaway right around the equator with some little continental blocks moving through it, including the South China Block, which is where I've done a lot of my work studying the end Permian extinction. The event is way too fast for continents to reorganize. And so the continents, even if you looked at a time lapse for 1 million years, the continents aren't doing much. They're where they're at. But this giant volcanic province is erupting, emitting these huge amounts of gas. And, in some short interval, certainly less than 50,000 years, maybe less than 10,000 years, biodiversity collapses. And we don't know because when you get down to those timescales, our radiometric clocks aren't good enough. Like we can't tell the difference between 1,000 and 10,000 years. So we don't know the exact timescale, but we know it's very fast. There's this huge collapse in biodiversity, followed probably by another further collapse in biodiversity 100,000 years later, 50 or 100,000 years later. There's a huge change in climate. In the long-term sense, the Earth gets much warmer. It's possible that for a very short period, it got much colder from the sulfate aerosols. Based on really clever new techniques that have been developed, we've been able to show by changes in the amount of uranium in the rock and the ratio of uranium-238 to 235 that the amount of oxygen in seawater declined a lot. And this is consistent with more basic geological observations and even with some biological observations of what kind of organic molecules do we find. And we find some organic molecules of some of these photosynthesizing bacteria that operate in the absence of oxygen. That doesn't mean the atmosphere lost oxygen. Sure. It didn't. What it means is that there were probably shallow parts of the ocean where there was enough decay of organic matter that used up all of the oxygen, but there was still light coming in. And so when all the oxygen's been used up, there's light coming in and you've got sulfide there. These bacteria that used to be very, very important suddenly become locally important because of this big environmental change. And so for this end Permian, we've been able to put a lot of these pieces together. In terms of the climate change, we are able to measure essentially things that are similar to our teeth or the teeth of fish from an ancient group of animals called conodon animals. And when we measure the oxygen 18 to oxygen 16 ratio, we get a measure of the temperature of the water in which they were living. It's a little, as with all these things, it's a little more complicated, sure. But it does give us a quantitative measure of temperature change. And it looks like the Earth warmed up by about as much as 10 degrees Celsius at this time.
Instantly.
From a geological perspective, instantly.
Okay.
It doesn't mean that at the start of our podcast and the end of the podcast, sure. We increased by 10 degrees Celsius. But it means that may have happened over a time scale of, say, thousands or a few tens of thousands of years. And in fact, if you try to do it over longer time scales, it gets a little harder because the geological processes that act as Earth's thermostat try to dampen that down. And so one of the really interesting problems after the end Permian extinction is it looks like the Earth stays warm for a few million years. That's a little bit contrary to how we understand the Earth's climate system to work. And so one problem that those of us who spend our lives thinking about the end Permian extinction worry about is, how do you keep the Earth warm for that long? What set of processes do it? Is it a failure of the temperature regulating mechanisms that you run out of rocks to weather, for example, and you don't have enough tectonic uplift? And so essentially everything gets covered in an unreactive soil would be a way of thinking about it. Again, that's simplifying, but that's sort of the general idea. Another possibility would be maybe something happens as you get into this warm state that, say, increases methane concentrations in the atmosphere and holds them high, and that keeps the Earth warm. And so maybe it changes the albedo, right? Maybe the Earth goes into a state where it absorbs a lot more sunlight than it used to. And so we don't understand, I don't think yet, the technical processes, but we know what the problem is. We know that we have an Earth that warms up by a lot, and instead of cooling down, so if we look at a more recent event, like there's an event called the Paleocene-Eocene thermal maximum 55 million years ago, also volcanic, also shows very rapid warming. It then shows this exponential gradual cooling over the next 100 to 200,000 years. The end Permian, and that's sort of how we understand the geological processes to work normally. So the end Permian is sort of this puzzle where it warms up and then it looks like it stays warm for a few million years. And this, again, for modern climate, a big question would be, again, this doesn't apply really on the century time scale, but as we think out farther, a question would be, if anthropogenic CO2 emissions lead to a much warmer climate, as they're already doing, do the natural processes kick in and cool us back down eventually? Or does something happen that shifts the climate to just a new state where it's perpetually warm? And that would have very different consequences than expecting eventually geological processes to save the planet, even if humans aren't able to save it beforehand.
John, you got to go in 4 minutes.
No. Okay.
But I'm going to throw, a couple of observations and questions, and we can use that as a conclusion. Is there enough evidence in terms of chemical weathering as for humanity to be worried about potential mass extinction?
Yep.
And then how do you deal with the kind of denialism, with respect to climate change? And last would be, as of yesterday, the United States government decided to pull out of the Paris Accords.
Yeah.
How do you put all those together?
Right. So I'll try to stick to the things I know well.
Sure.
So what I would say is the geological record tells us a few things, right? One, it tells us that mass extinction does happen and that massive climate change does happen. There's no reason for us to sit around thinking these things can't happen. They do, and they have. Another thing I would say is that timescales matter a lot. When we look at these mass extinction events, the recovery of climate takes hundreds of thousands of years, sometimes millions of years, like the end Permian.
Right.
The recovery of biodiversity takes longer. It almost always takes millions of years, sometimes verging up to 10 million years or more. And so if you intend to be around for 100 million years, natural processes will solve these problems. The climate will recover. Biodiversity undoubtedly will rebuild in some new way. If you care about your kids and your grandchildren and their children, geology is not going to save us. The processes are not fast enough. And so anything that we do as humans is permanent on the timescales of our own lives. It's, in terms of, causing climate warming, causing biodiversity loss. These are essentially permanent problems on the timescales of our lives. They're permanent on the timescales of any of our descendants that we can easily imagine, right? Our kids, our grandchildren, our great-grandchildren, and any of our descendants that we might plausibly hope to meet will live on a different planet from the one that we live on as we change it. Even on the timescale of nations and societies, right? So U.S. has been around more than 200 years. Some of our more ancient societies, let's say maybe a few thousand years. Essentially, a way to view it is, for sort of the kinds of stuff I was taught, right? Think about the ancient Egyptians building the pyramids. If we go that much farther forward in history from the Egyptians to us, those people will still be living with the consequences of our decisions in 2,000 years, for sure. And so it's up to us to save us. Geology is not going to save us, even though, yes, we will not eliminate all life from the planet. I don't think that'll happen. Eventually, natural processes will take control of climate again, but they will not do it in our lifetime. And they will not do it in the lifetime of the nations that we belong to. And so the solutions that we care about are going to have to come from us.
Are you optimistic about human behavior?
I am. I think that in lots of ways, we have improved the lives of people. I think very few of us would want to would trade the life we have now to be assigned to be a random person 500 years ago or 1,000 or 10,000 years ago in the absence of antibiotics, in the absence of routine. I was born by cesarean section, right? I would not be alive without modern medicine, right? I've had multiple, I've had strep throat, I have a lot of bacterial infections that would have killed me in an ancient world. I've been able to travel and see the whole planet, right? That was impossible to all but a few people even a couple centuries ago, right? Most of us live much better lives now than people did hundreds and thousands of years ago. In many ways, life is better now. Doing that has had consequences, right? People didn't start exploiting coal and oil and gas in order to create climate problems, right? They did it to bring people out of energy poverty. And nobody wants to go back to energy poverty, right?
Sure.
What they didn't appreciate, but have started to appreciate, is the climate consequences of that, and the fact that you create new problems in solving old problems. I think we've spent much too long with at least some groups denying the important impacts of CO2 emissions and other things. We have to acknowledge those, and we have to solve them, right? And my optimism is, I think that despite efforts at denialism, more and more people understand and acknowledge the consequences of burning fossil fuels.
Yep.
More and more people that I see want to use the technical expertise, the training that we're giving them, to figure out how to solve them. And I think that what I would say is, when I'm not a historian, but I've taken a number of history classes, and certainly what I can see, is these things are not linear, right? That the life I live in, my great-grandparents, some of whom I met when they were kids, they could not imagine the world that I live in. And so I don't think that I can easily imagine the world that my great-grandchildren will live in. That could be a very bad thing, right? It could mean that the world's going to be much worse than I can possibly imagine. But I like to think that it also means that the world could be much better than what I imagine. That technologies, when I think about ChatGPT, right? There are technologies now that I couldn't have imagined 10 years. It seemed like science fiction 10 years ago, right? My hope is that in addition to developing things like social media, that our most talented people will turn their attention toward technologies that can solve real problems that will make everyone's lives better.
Amen.
And I'm optimistic. I think we can do it.
Thank you so much, Sean.
Yeah. Thank you for having me.
Thank you. That was Professor Jonathan Payne from Stanford University. Thank you.
Inilah Endgame.